Let's start with the first one. Leanne, the floor is all yours.
All right, thank you. Good morning, everyone. My name is Leigh and Zhang, and together with me is Chris Nelsen. We're both from Delve Underground. Let me turn my camera on really quickly. So before we dive into our presentation, we'd just like to quickly acknowledge that this paper was first written and presented for NAT 2022 conference that was held in Philadelphia. We appreciate the opportunity the organization has given us to present our paper in front of our industry peers. Now, without further ado, let's dive into our presentation. Hybrid shoring design for the Courthouse Commons Tunnel in San Diego, California, controlling and predicting ground movements. This was the title of our paper. Today, during our presentation, our purpose is to walk you through a case study of a supportive excavation wall deflection analysis and its correlation to the observed ground movement supported by instrumentation data. We hope to demonstrate through this presentation the value of the instrumentation program to a successful project. Such values include, providing a reassurance to the owner and the project team that the design safety criteria has been met, and furthermore, provide confirmation to the major design assumptions and point out any conservatisms that might be built in the design that can be used as future design enhancements. Going through a quick agenda of today's presentation. First, we're going to go through a project overview. Next, we're going to introduce you to the ground movement instrumentation program implemented for the project. Then I'm going to talk a little bit about the wall deflection criteria analysis and its discussions. Then Chris is going to lead the section on settlement analysis discussions. And lastly, we'd like to share a few lessons we learned from this project. So Courthouse Commons Tunnel Project. It is located in downtown San Diego. Now, I would like to take your attention to the right side figure. This shows the main components of the project. We have a pedestrian tunnel that connects the county jail and the new courthouse. It also crosses a heavy city block. And as the inlet of this pedestrian tunnel is the transfer facilities shaft. This is currently marked with the red star, and this is the main subject of our presentation. So bring your attention closely to the transfer facility shaft plan view. The purpose of this transfer facility shaft excavation supportive system is to, one, provide a safety environment for the excavation, two, to protect the adjacent structures, namely the county jail, the old jailhouse and courthouse, and three, provide a tunnel excavation launching point. On the screen, what we wanted to highlight is that we have a very congested site to work with. Our transfer facility shaft is situated right next to the county jail on an active street. On the right side figure, you can see that we have our crane located very close to the existing building. There is very limited amount of area to work around with, and we have a lot of heavy equipment. The next figure shows a picture that was taken during the construction of the shaft. You can see that the supportive excavation walls are already installed. The internal bracings are also installed, and we have some HVAC equipment. Again, there is very limited space to work around, so very congested. Lastly, I just wanted to touch on the dimensions of our shaft. It is approximately 18.5 foot in width, 52 feet in length, and 56 feet in depth. So the supportive excavation system for this transfer facility shaft is particularly challenging because of the county jail that sits on the east side of the shaft. This county jail is an 11-story building that sits on a mat foundation, and the primary purpose of it is to host inmates. So the county jail structure is unique in a sense that it's very sensitive to any settlement that's induced by adjacent excavation activities and the settlement criteria for this reason was given to be very low. As a structural designer, we need to translate the settlement criteria into a wall deflection criteria for it to be meaningful to the design. To do so, we have two major assumptions. One, the site was dewatered prior to excavation activity, and we conservatively assume the settlement induced by dewatering activity to be about 1/4 inch. Next, we were given that the assumption that for 1 inch settlement, there will be expected to be 2 inch of wall deflection. So plugging all these numbers in, we arrived at a wall deflection criteria of 1.5 inch for the north-south-west wall, which are the walls that sits on the street, and 1 inch wall deflection criteria for the east wall, and that is the shoring wall that's directly facing the county jail. Just taking a step back, we were originally given a total allowable settlement for the north-south-west wall as 1 inch, and for the east wall, the total allowable settlement was 3/4 inch. These values are considered very small given the size of the shaft and the loading demand that the shaft has to be designed for. So what did we come up with? We worked closely with the contractor to come up with a hybrid system that both meets the safety requirement of the project and at the same time is cost effective. For the shoring walls, we utilized a C-compile wall for the east wall. This is the side that directly faces the county jail, and C-compile wall is a more rigid system that is good to control wall deflection. However, it is more costly, so we come up with soldier pile and lagging wall, which is a less expensive solution for the west, south, and north walls that are facing the streets where the deflection criteria is larger. For internal bracing systems, we come up with 3 levels bracings and finally a temporary structural slab at the bottom of the shaft. We wanted to mention that during design iteration, we also deleted cross bracings for the internal bracings. Cross bracings are usually, you can usually see them at the corner of these internal bracing systems, and we eliminated them to allow the contractor more construction clearance to move their equipment around. Next, going to the construction sequence of the shaft. As mentioned before, the site would be dewatered prior to excavation. Then we continue to excavate to just below each internal bracing levels. We install the bracings until we reach the bottom of the shaft. We install the temporary structural slab, and then the shaft is backfilled to just below the level 3 bracing. The level 3 bracing is then removed because it is at the same elevation where the tunnel breakout face is, so it needs to be removed to allow the tunnel excavation to commence. The dewater system is, during design, we assumed that the site will be dewatered to be 3 foot below the bottom of the shaft. Next, going to the instrumentation program. What you see on the screen is showing the pedestrian tunnel and the transfer facility shaft. The red dots are the various instrumentations that we designed for the project. We're going to focus in the red squared area where the instrumentations are relevant to the discussion of the transfer facility shaft. So what are these instrumentations? We have inclinometers that are installed on the west side and the east side of the shaft. These are manually read. We have liquid level sensors that are installed in the existing county jail basement. These are automatically read. And lastly, we have high-level sensitivity settlement system also installed in the county jail basement and are also automatically read. Just going through the wall deflection analysis briefly, that was implemented during design. Typically, we would perform a single-staged deflection analysis to arrive at the anticipated wall deflection of the entire construction. However, given the stringent wall deflection criteria of this project, we felt that a cumulative deflection analysis was needed. This cumulative deflection analysis takes every single stage deflection analysis and superimpose them onto each other to arrive to capture the deflection of the wall during the entire construction activities. Just quickly touching on some of the major assumptions that we had for the cumulative wall deflection analysis. The first one is we assume that any deflection occurring at the wall will be locked in at an internal support level, namely where the bracings and slabs are installed. Next, we assume that the deflection between any of these two support points is going to be unrestricted. In the table below, this listed our final estimated maximum cumulative wall deflection for each side of the wall during design. You can see that for the east wall that is facing the county jail, we anticipated 1 inch of wall deflection. And then for the soldier piles on the north, south, and west side, we anticipated 1.08 inch and 1.14 inch respectively. On this slide, what you're seeing is the expected wall deflected shape during design plotted against the observed wall deflected shape as reported by the inclinometer data during construction. These plots are produced for the west wall, that is the long wall facing the street, and the wall system is soldier pile and lagging. On the x-axis, you're seeing the deflection of the wall, and any positive readings are indicating the wall is deflecting into the excavation opening. Any negative reading is indicating the wall is moving away from the excavated opening. The y-axis represents the depth of the wall. So the colorful, just the last point to guide you through reading these plots, the colorful lines represents the inclinometer data as reported from the site, and the black dashed line represents the expected wall deflected shape during design. We wanted to show that, as you can see, the inclinometer data appears to agree with the anticipated wall deflected shape well, and our wall anticipated shape are showing that at the bracing levels, the deflection are locked in, and we're observing the pile fixity, which occurs at the bottom of the wall, seems to agree between the analytical results and the observed inclinometer data results. On this slide, you're seeing similar plots, but this time for the east wall, which is a secant pile system. Again, you can see any positive deflection readings represents the wall movement into the excavation opening, and any negative reading represents the wall deflection away from the excavation opening. What is interesting here is we have observed, based on inclinometer data, that the east wall appears to be moving away from the excavated opening, especially towards the a shallower part of the shaft. And we looked at these plots, and in our minds, we were trying to think about what could explain this phenomenon. And we think this is because on the east side, just between the secant pile wall and the existing county jail is the county jail basement. And this county jail basement, in theory, does not contain any ground, and therefore does not oppose any load to the secant pile system. However, on the opposite side of the shaft, we have the street where the soldier pile and lagging system sees the full load. And this loading was transferred by the internal bracings in a way that the street is pushing onto the soldier pile and lagging wall through the bracing to the secant pile. And that's why we're seeing the secant pile wall deflecting away from the excavated opening into the county jail side. So observations and discussions, we had touched on some of them already on the previous slides, but again, we just wanted to iterate that our analytical results seems to envelope the observed data well. We're also confirming that our pile are pinned at the supports, and we are observing a continued deflected shape past the support points. We confirmed our assumption about the location of pile fixity in the ground. However, we do recognize by the inclinometer data that there are certain level of conservatisms built into our design. These conservatisms include a 2D versus 3D load transfer. During design, we assumed that the load transfer is completely two-dimensional. However, we recognize that at the corner of the shaft, a 3D load transfer might be occurring. And the second conservatism is that we completely ignored the confinement backfill provides within the shaft during construction, and that could help restricted any pile movement into the excavated opening. And lastly, we ignored the cohesion in the soil, which may have resulted in a less loading demand and help with controlling the wall deflection during construction. In the table here, you're seeing the wall deflection criteria that was shown on one of the earlier slides, the maximum cumulative deflection that is anticipated for each type of the wall during design, and lastly, the maximum observed deflection as reported by inclinometer data on site. What's interesting here is the maximum observed deflection as reported by inclinometer data is obviously much lower than that anticipated during design, but we think that, our final result is that they meet the wall deflection criteria that was given, and we delivered a successful project to the owner, and that is also cost effective for the contractor to build. Next, I'm going to hand off the section to Chris. Chris, please take away.
Here we go. All right, thank you, Leanne. So I'll start this half of the presentation by reviewing the site geology for the Courthouse Commons Tunnel and follow up with a discussion on the pre-construction settlement analyses that were performed and a comparison to the observations of those settlements during construction. And lastly, I'll go over some of the lessons learned from this project. So first, the site geology consisted of three main layers, as we can see on this slide. Below the ground surface, there's about 10 feet of artificial fill, followed by 5 feet of alluvium. Both of these deposits are relatively soft, as indicated by the low blow counts seen in the figure on the right. These upper layers are then underlain by the old Paraluk deposit, formerly known as the Bay Point Formation, which is a weakly cemented, dense to very dense, coarse grain material. And then you can also see the existing groundwater table is at approximately the tunnel springline elevation. And as Leanne mentioned, it was dewatered to 3 feet below the shaft for the duration of construction. There we go. So to begin the discussion about settlement analyses used on the project, we first need to look at the potential sources of settlement, as Leanne mentioned, so I'll go through this fairly quickly. There are three potential sources. There's settlement due to the tunneling, settlement due to the lateral deflections of the supportive excavation system, and settlement due to dewatering. Leanne already covered the settlement due to dewatering, which was estimated to be approximately 1/4 of an inch. And tunnel construction occurred after shaft construction, so the settlement due to tunneling is not included in these analyses. And that leaves us with the settlement due to the lateral deflection of the supportive excavation system. So estimating settlement of structures in the vicinity of deep excavations has really been a challenge for engineers that we've been dealing with for years. There are a number of different approaches out there. However, the accuracy and conservatism of these methods for different types of projects are still debated widely. And among these methods, we can look at empirical or analytical methods, numerical methods, and rely on local experience as well. So in this project, we initially used the Peck method and the Clough and O'Rourke method to determine the maximum settlement. However, the values for these methods seemed overly conservative and we wanted to look for another option. And as a result, Kleinfelder, the geotechnical engineer for this project, proposed that we use half of the maximum lateral deflection as the maximum settlement based on their local experience in San Diego and Southern California on similar projects. And I'll note that we did not use numerical methods for this purpose at the time, but this is captured in one of our lessons learned at the end of the presentation. Looking at the first two empirical methods that we used, Peck's method is a factor of the soil type at the structural location, zones 1, 2, and 3 on the plot to the left. Zone 1 is where we fall for this project due to the very dense coarse grained material of the old Paraluk deposit, with blow counts exceeding 40 blows per foot. And Peck conservatively sets this line as the upper bound for sandy material, which results in an estimated maximum settlement of 3.8 inches. As this is grossly over-conservative, we then looked to the Clough and O'Rourke method, who plotted the maximum soil settlement as a function of depth of the excavation, as seen in the plot on the right. So most of the data falls along the line that corresponds to a maximum settlement of 0.15% of the excavation depth, which results in an estimated maximum settlement of 0.7 inches. And this was judged to be a much more reasonable estimate of maximum settlement that we used moving forward. And to further refine those estimates, we decided to go with the local experience that I previously mentioned. And based on that local experience, we assume that the maximum settlement at the face of the shoring is half of the lateral deflection at the face, as determined by the cumulative deflection analyses presented by Leanne in the previous slides. So these values then read as 0.53 inches for the secant pile wall on the east and 0.75 inches for the soldier pile and lagging wall on the northwest and south. And these are similar values to the Clough and O'Rourke method, so we're pretty happy with these assessments. In order to determine the magnitude of the settlement away from the face of the wall, we went back to the Clough and O'Rourke method for sandy material, as shown in the upper right-hand corner of the figure. And this method normalizes the settlement based on the maximum settlement as a function of distance from the wall face, which is illustrated on the plot to the left. So these two lines represent the conservative envelopes to bound the settlement estimates as a function of distance from the shoring. So moving into the settlement observations, we relied on two main types of instruments to measure the settlement during construction. On the west wall, again, the soldier pile and lagging wall adjacent to the road, there were two rows of surface settlement points at 6 and 21 feet from the wall face, and these were monitored with an automated total station. On the east wall, the secant pile wall adjacent to the county jail, there were 3 rows of liquid level settlement sensors at 5, 22, and 42 feet from the wall face. So starting with the east wall, which supports, again, the county jail and a very high surcharge load, this plot shows the measured settlement for the row closest to the county jail wall face. The date range corresponds to the full duration of the excavation, all 5 stages that Leanne discussed, and overall there's very little settlement, a maximum of just 0.03 inches. Still looking in the basement of the county jail, the plot in the upper right shows the settlement for the middle row, 22 feet from the wall face, and it shows more settlement, about 0.2 inches, but still very low settlement as compared to the upper bound envelopes from the pre-construction analyses. And you'll see the one malfunction in the liquid level points that were damaged during construction and had to be replaced in early August. After the instruments were replaced, the readings continued along the previous trends. And the plot in the lower left shows the instruments furthest from the wall, or 42 feet from the wall face, showing a maximum settlement of 0.07 inches. We see very similar results looking at the west wall, which consisted of the soldier piles and lagging. And as a reminder, these points were measured with surface settlement points and an AMTS unit. Most of the movement occurred 6 feet away from the wall face during the cantilever stage. And the maximum settlements are also measured from a non-zero starting point due to the slight movement that occurred prior to shaft excavation. But overall, the measured settlements for 0.1 inches and 0.07 inches at 6 feet and 21 feet from the wall. So finally, comparing the predicted settlement to the observed settlement, we can see that the pattern observed from the secant pile wall shown in the red dots on the plot to the right, is similar to the Clough and O'Rourke settlement trough shown schematically on the left, but it's still very conservative. Overall, the project data is bounded by the predicted movements based on local experience and the Clough and O'Rourke method. So we stayed within those bounds for a successful and safe project. The last, there are lessons learned overall. The first point, that improvements can be made in the structural analysis by considering 3D load sharing effects for these for shafts of these dimensions. Second, the available theoretical and empirical methods to estimate settlement of structures in the vicinity of deep excavations are generally over-conservative, and using numerical modeling will help determine the settlement more accurately. Third, taking into account the corner effect of the shaft adds to the accuracy of the settlement determination, especially in the shafts of dimensions of this type. And lastly, in agreement with the theme of these webinars, the geotechnical instrumentation that was used during construction really gave us as the engineers and the owner confidence in the project and valuable insights looking forward to similar projects in the future. And with that, I'll wrap up a couple minutes early. And we'll just, again, we'd like to acknowledge a couple authors who were part of this paper and part of the project: Mark Lawrence, Miriam, Jeremy, John Stoltz, and Yiming Sun as well. So thank you again, and thank you for your attention.
Thanks, Chris. Thanks, Leigh, for the presentation. One question that I have, and it's kind of personal. You know that I'm a strong believer in CPT. Was the use of CPT at all considered to determine the settlement? Because of course you can derive settlement from CPT data. Was it considered, or was it not thought of during this project?
Leanne, I might defer to you on that one. I'm not sure if CPT data was available to us when we were brought on board, if it was done by the owner or previous designer.
Yeah, that's a good question. Thank you. I would have to say that based on my recollection, we weren't provided CPT data at this project.
Not surprising, but you're talking to a conehead, so that's definitely something that I just had to mention as well. Thank you for a great presentation to both of you. There's some questions coming.